Welcome to the basic thermodynamics class. So, second chapter thermodynamics process. So, in that we are discussing about the polytropic process and the numerical problems in this class. So, move on to the next slide. In this class we discuss about the expression for the work done during the adiabatic process and the relationship between the pressure, volume, temperature. Next, adiabatic index and some problems related to the adiabatic process. So just I'm giving what I'm just giving the formulas for the work done during adiabatic expansion, that is P1 V1 minus P2 V2 by gamma minus 1, where gamma is the adiabatic index. Gamma is adiabatic index. So gamma is equal to Cp by Cv, the ratio of specific heats at constant pressure by specific heat at constant volume, and R is equal to Cp minus Cv. R is equal to Cp minus Cv. And the work done during the adiabatic compression, it is P2 V2 minus P1 V1 by gamma minus 1. Gamma minus 1. And here what is an adiabatic process means, in the adiabatic process the heat transfer is 0. Heat transfer is 0. Non-flow energy equation dq is equal to du plus dw, dq is equal to 0. So du plus dw is equal to 0. Then get the internal energy, dw is equal to minus du. So here the work done during expansion process, the internal energy is decreasing. Internal energy is decreasing. In compression, internal energy is increasing. Compression, the internal energy increases. So the relation between P, V and T is a P1 V1 gamma is equal to P2 V2 whole power V2 power gamma. P1 V1 power gamma is equal to P2 V2 power gamma, and the relation between volume and temperature is T1 by T2 is equal to V2 by V1 whole power gamma minus 1. T1 by T2 is equal to V2 by V1 whole power gamma minus 1, and the relation between the pressure and temperature are T1 by T2 is equal to P1 by P2 whole power gamma minus 1 by gamma. So these are the relations between P, V and T, and we solve some numerical problems on an adiabatic process also. Next, so in this class we will discuss about polytropic process and the expression for the work done and the heat transfer during the polytropic process, and the problems related to the polytropic process. So general form of the equation for the pressure volume relationship can be written as a PV power n is equal to constant. So in adiabatic process, so we written as a PV power gamma is equal to constant, whereas in the polytropic process we are writing the relation between pressure and volume as a PV power n is equal to constant. Here the n is called a polytropic index for the compression or expansion. N is called the polytropic index for a of compression or expansion. So in many thermodynamic process, the conditions for the constant temperature and the adiabatic process cannot be, are never achieved, and are never achieved. So that's why, and the pressure and the volume relationship can be described by the equation PV power n is equal to constant. So such that the process is called a polytropic process, and n is called a polytropic index or the polytropic exponent. You can call it as a polytropic index or polytropic exponent. So this is the relationship between the pressure and volume. PV power n is equal to constant. So where n is equal to polytropic index or polytropic exponent. So here in the polytropic process, the both the work and heat energy may be transferred across the boundary. In both the work and heat energy may be transferred across the boundary. So you have to remember that first. Whereas in the adiabatic process, the heat transfer is 0, But in the polytropic process, both the work and heat transfer is there. Both the work and dW is there and the dQ is there. Work and the heat transfer may be transferred across the boundary. So a process which follows the general law, that is PV power n, is called a polytropic process. And in polytropic process, both the work and heat energy may transfer across the system of the boundary. So this point is very important. Whereas in the adiabatic process, only the work may be transferred across the system and the heat transfer is zero. Heat transfer across the boundary is zero. In polytropic process, both the work and the heat energy may transfer across the boundary. Here is the expression for the work done. So there is no derivation required for you. Only the expressions are there. So we are considering the polytropic process equation by PV power n is equal to constant. PV power n is equal to constant. P is the pressure, V is the volume and constant. So we are considering the mass mkg of a gas at a conditions P1, V1, T1. So changes the conditions to the next P2, V2, T2. So according to the law, what is the law? PV power n is equal to constant. So the work done is equal to work P1 V1 minus P2 V2 by n minus 1. So this is a PV graph. This is a PV graph. As the volume is increasing, the pressure is decreasing. So first state here, the second state is whatever the work done is between the state 1 to the state 2. So PV power n is equal to constant. PV power n is equal to work done during the polytropic expansion process is P1 V1 minus P2 V2 by n minus 1. Whereas in the adiabatic process it is a gamma minus 1. Here the gamma is replaced with a polytropic index or a polytropic exponent, that is a P1 V1 minus P2 V2 by n minus 1, or this equation we can write as a MR T1 minus T2 by n minus 1. MR T1 minus T2 by n minus 1. So we can write this equation also like this. So this equation is due to expansion only. This equation is due to the expression for the work done during the polytropic expansion. Similarly for the polytropic compression. So W state 1 to 2 is represented as a P2 V2 minus P1 V1 by n minus 1. And we can write this equation as a MR T2 minus T1 by n minus 1. Same with the adiabatic process and the polytropic process are the same. In there are adiabatic index is represented here. Polytropic index here is a n. So same formula, work done for adiabatic and the polytropic. So here the index is different. There is a polytropic index gamma and here is a adiabatic index gamma. Here it is a polytropic index n. So this is the work expression for the work done during the polytropic expansion process, compression process, where n is the polytropic. Here the in adiabatic process the heat transfer is zero, but in a polytropic process there is a heat transfer is takes place. So further the expression is a Q is equal to gamma minus n divided by gamma minus 1 into MR T1 minus T2 by n minus 1. So this is nothing but the work transfer equation during the expansion process. So we are writing this equation as a gamma minus n into gamma minus 1 by into work done. See, this is the, so this equation represents the work done, expression for the work done during the adiabatic polytropic expansion process. That's the whole equation I am writing as a work done. So the expression for the work done is, heat transfer is a Q122 gamma minus n divided by gamma minus 1 into work done. So work done formula may be both we have two formulas. One is P1 V1 minus P2 V2 by n minus 1. Another one is MR T1 minus T2 by n minus 1. So in terms of a temperature, this is the equation. In terms of a pressure and volume, we can write them another equation also like that. So this is the expression for the heat transfer polytropic process. So next coming to the polytropic index. So polytropic index, for a polytropic index the value of n can be obtained by the value of n can be obtained by a parameters pressure, volume and temperature of any 2 points in the curve represents the polytropic process. So here we know that PV power n is equal to constant. For the state 1 to state 2 means I am writing here is a P1 V1 power n is equal to P2 V2 whole power n. P1 V1 power n is equal to P2 V2 whole power n. Now I am writing this equation as a taking logarithm on both sides. So I am applying log on both sides. Log E P1 V1 power n log E P2 V2 power n. So we all know that log AB is equal to log A plus log B. So we all know that what is the formula of the log AB, and log AB is nothing but log A plus log B. So first I am writing that here like this. So here I am here it is the form of a log AB. So I am writing log A and log B, log A plus log B. Here also log P2 plus log V2 power n, and here also power n is there, and we know another formula log A power m is equal to, we can write as a m log A, m log A. So we all know that log A power m is equal to m log A. So here I am writing this log E V1 power n as a n log V1, n log V1. So I am telling once again, here we all know that the polytropic equation is a P1 V1 power n is equal to P2 V2 whole power n. So here I am taking the logarithms on a both sides. So I am taking the log on a both sides. So apply log on both sides. Next, so we all know that log AB is equal to log A plus log B. So I am applying log P1 plus log V1 power n log P2 plus log V2 power n, and whole are the power base is a E. So that's why I am not telling. So for every both sides the base is a E. Base is a E. And after that here we have to also simplify here. Here it is a log E V1 power n. So we all know that log A power m is equal to m log A, m log A. So I am writing here like that, log E P1 plus n log E V1 is equal to log P2 plus n log V2. Next, what is the next step here? I am bringing this n on one side and without n P on one side and the volume on one side. So I am n n log E V1 minus n log E V2 log P2 minus log P1. I am bringing the pressure in one side and the volume as another side. In volume we have n. So I am taking as a n as a common. So if you take as a n as a, because we want the polytropic index value n value, that's why we are taking n into n as a common and bring this term, bring this log E V1 minus log V2 into this side. It comes into the denominator, or, and we know one more formula also, that is log A minus log B is equal to log A by B, and we also know that log A minus log B is equal to log A by B. So I am writing this here like that. Here it is a log V1 minus log V2. So I am writing this log E divided into V1 by V2, and here log E P2 by P1, P2 by P1. So bring this log V1 by V2 to this side. So then it becomes as a n log, n is equal to log E, base E is important here, base E P2 by P1 divided by log E V1 by V2, V1 by V2. So if you remove, if you don't want E, so you want as a base 10, we can write it as a log log E we can write as a 2.3 log base 10. Log E we can write as a 2.3 log base 10. So both in the numerator 2.3 is there, denominator 2.3 is there. So it get cancelled. So we can write as a n is equal to log 10 P2 by P1 log base 10 V1 by V2. We can write anything, P2 by P1 or V1 by V2, or we can write this equation as a log E P1 by P2 divided by log V2 by V1. We can write anything like this, or P1 by, we are interchange this P1 by P2 and denominator also V2 by V1. So n is equal to log E P2 by P1 log V1 by V2, or base 10 also, 2.3 2.3 will get cancelled and the remaining is log base 10 P2 by P1 base log base 10 V1 by V2. So this is the polytropic. So here in adiabatic process, there is a relation between pressure, volume and temperature. Similarly, there is a relation between the similar way to the adiabatic process. The polytropic process also have the relation between P, V and T. Simply whatever the relations in the adiabatic process, we are replacing that gamma in terms of gamma with n, gamma with n simply. So we know that P2 P1 V1 power gamma is equal to P2 V2 power gamma. Simply we are replacing gamma with n. So then the relation becomes as a P1 V1 power n is equal to P2 V2 power n. Like that, T1 by T2 is equal to V2 by V1 whole power n minus 1, and T1 by T2 is equal to P1 by P2 n minus 1 by n. So the relation between P, V and T for the polytropic process, same as an adiabatic process, they are simply replacing gamma with an n. So T1 by T2 is equal to V2 by V1 whole power n minus 1 is equal to P1 by P2 n minus 1 by n. Here n is in a polytropic index, whereas in the gamma is in adiabatic process, so that's why it is called an adiabatic index. So in this you have to remember total three formulas. So what is the first one is a work done, next one is a heat transfer, next one is a polytropic index, and next one is the relation between the P, V and T for a polytropic process. So first we have to remember what is the expression for the work done in expansion process is W is equal to P1 V1 minus P2 V2 by n minus 1, or in terms of temperature means MR T1 minus T2 by n minus 1. This is the work done for the expansion process. Next, for the work done for the compression process means W is equal to P2 V2 minus P1 V1 by n minus 1, or we can write MR T2 minus T1 by n minus 1. Next, Q. Here in the polytropic process, both the work transfer and the heat transfer is takes place. So Q is equal to gamma minus n by gamma minus n divided by gamma minus 1 into work done. So work done we can write in terms of a volume, pressure and volume, or in terms of a temperature. So whatever the data given in the problem, based on the data we can write the formula. It depends upon the volume, pressure and volume is we write the formula based on a pressure and volume. If they given the temperature values, we can write the work done as a MR T2 minus T1, that formula. Next, coming to the polytropic index. So n is equal to log P2 by P1 divided by log E or base 10. Log base E or base 10, we can write anything. If you write the numerator as a P1 by P2, and we can write denominator as a V2 by V1. Or if you write the numerator as a P2 by P1, we can write the denominator as a V1 by V2. So log E can be replaced with a 2.3 log 10. So both numerator and denominator has a 2.3, 2.3. So both will get cancelled and remaining is a log base 10. So that is the polytropic index n value. Like that, the relations between P, V and T. So T1 by T2 is equal to V2 by V1 whole power n minus 1, and P1 by P2 is equal to P1 by P2 is equal to T1 by T2 whole power n by n minus 1, or T1 by T2 is equal to P1 by P2 whole power n minus 1 by n, or P1 V1 power n is equal to P2 V2 power n. Okay, we can write like anyways. This is the relation between P, T, V. Same in adiabatic process, it is replaced with an gamma is replaced with an n. Gamma is these are the formulas. Work done. P1 V1 minus P2 V2 by n minus 1, heat transfer, gamma minus n by gamma minus 1, nothing but the work done. So the relation between temperature, pressure and volume, already told that T1 by T2 is equal to V2 by V1 whole power n minus 1 is equal to P1 by P2 whole power n minus 1 by n. So this is the relation. So based on these four formulas, we will do the problem. These formulas based on the above four formulas. A gas initially at 603 Kelvin expands until its volume is 5.2 times the initial volume according to PV power n is equal to constant. So here they given that it is a PV power n is a constant, they given it is a directly, it is in a polytropic process. They didn't mention it is in a polytropic process, but they given a condition that is a PV power n is equal to constant. By seeing that condition, we can identify that it is in a polytropic process. So if the initial and the final temperatures are observed to be 8.5 bar and the 1 bar, determine the index of the compression. So index of the compression is nothing but the, you can calculate the n value. N is equal to question mark work done per kg of gas, W, heat exchange per kg of gas, that is Q. They given the CV value and gamma value. So first read the question carefully and identify what is the process and write the formulas related to that process. Here they asked to calculate the index of compression, means you have to write the formula of En and the work done W formula, heat exchange formula, Q. So the gas initially at 603 Kelvin temperature T expands until its volume is 5.2 times of initial volume. So V2 is equal to 5.2 of V1. They given the condition, it is a V2 is equal to 5.2 of V1 according to the PV power n is equal to constant. So these condition states that it is in a polytropic process. So if the initial and the final pressures, so they given the P1 and P2, here the pressure is decreasing and the volume is increasing. Determine the N value, W value and the Q value. They given the CV value and gamma value. So by using these values we can find the CP value and the R value. CP value and write the given data. T1 603 Kelvin, V2 condition they given, it is a 5.2 times of a V1 process polytropic expansion, P1 8.5 bar. So we all know that, so 8.5 bar we can convert it into 100 kilonewton per meter square. P2 1 bar 1 into 100 kilonewton per meter square. So first write the given data and write the whatever the formula is asked in the question. So CV 0.712 kilojoule per kg Kelvin, gamma 1.4. So index of expansion. So index of expansion is nothing but n is equal to log P2 by P1, log P2 by P1 divided by log E V1 by V2, log V1 by V2. Substitute all the values of, they given the P2 value and P1 value, can substitute directly, and they given the V2 is a 5.2 times of V1. So that's why I am substituting V1 directly and V2 as a 5.2 V1. Here then the numerator and the denominator V1 get cancelled. So by using the calculator, first calculate, put log E ln is there in your calculator. Type ln bracket open 100 by 850. So write that value in a numerator and divide it by log v1 by 5.2 v1. And so many students did one mistake here. So what is that mistake means? They will cancel v1 by v1. After cancelling the v1, they forget here it is in a numerator, and in numerator if v1 is get cancelled, there is a one value is there. This 1 into v1 we can write. So there is a 1 divided by 5.2. But so many students did the mistakes like they will continue calculations like a log e 5.2. Log e 5.2 is not correct. It is a log e 1 divided by 5.2. We have to calculate like a log ln bracket open 1 divided by 5.2. Here the 5.2 is in denominator, not it is in a numerator. In numerator v1 and v1 will get cancel. After get cancelling, here it is remaining, it is in a 1. So first by using the calculator, first calculate ln 100 divided by 850, right, equal to that answer, divided by, here in numerator v1 is there, denominator v1 is there. After getting cancel, here it is, there is a 1 divided by 5.2. So ln 1 divided by 5.2 is a n value is a 1.3. Adiabatic index value is a 1.3. Next, what they has the work done per kg of gas. It is in a polytropic expansion process. So P1 V1 minus P2 V2 by gamma n minus 1. So first of all, let us find the final temperature. So before calculating the final temperature, we all know that R is equal to Cp by Cv. R is equal to Cp by Cp by Cv. So calculate the Cp value by using gamma is equal to Cp by Cv. We will get one answer and substitute here, and they in the problem they given the Cv value also. Calculate that Cv value also. We will get both R value, Cp value and Cv value. First calculate by using the adiabatic index value. First calculate the Cp value. Cp is equal to 1.4 Cv. So Cv value already they given that. So Cp is equal to 1.4 Cv. Next, already Cv value is mentioned in the data. So we will get the R value. R is equal to 0.4 into 0.4 into 0.712, that is 0.2848 kilojoule per kg Kelvin. So both the Cp and Cv are in kilojoule per kg Kelvin. So R value should also be in a kilojoule per kg Kelvin. And we know the relations between the temperature and the pressure in a polytropic process, that is T1 by T2 is equal to P1 by P2 whole power n minus 1 by n. So in the problem they given the only T1 value, they didn't given the T2 value. So we have to calculate this T2 value. So T1 by T2 is equal to P1 by P2 whole power n minus 1 by n. Substitute the T1 value by T2 in denominator same as it is, P1 value and P2 value, and the n value we got in the A bit, that is a 1.2, 1.2 minus 1 divided by 1.2. So like this, 603 divided by T2 is equal to 850 divided by 100 into power 1.3 minus 1 divided by 1.3. So first calculate this part. First calculate this part. So first calculate 850 by 100 means 8.5. 8.5 whole power 0.3 divided by 1.3. So 8.5 divided by, so 8.5 power 0.3 divided by 1.3. We will get one answer. So write here. After that, bring this 2 to the right hand side, and whatever the number this side, bring to the right hand side, left hand side to the denominator. So 603 divided by whatever the answer you got, bring to the denominator here, and that one is the T2. T2 is a 369 Kelvin. So work done is equal to P1 V1 minus P2 V2 by n minus 1. So we all know that the P1 value and P2 value, and we don't know the V1 and V2 value directly, and they given the V2 value is the ratio of a sumdance event, but we know we can use another formula also, but we know the temperature T1 and T2. So I'm writing that formula because I have the data of about the temperatures T1 and T2. In this I don't have the data about the V1 and V2 separately. Here they given the ratio about the V1 and V2, so it is little bit difficult to solve the problem. That's why I know that temperatures T1 and T2. That's why I'm using the formula W122 MR T1 minus T2, MR T1 minus T2. So they asked to calculate the work done per kg of gas, means M is nothing but the 1 kg. R value we calculate, T1 and T2 also we got in the first step. So MR T1 by T2 divided by N minus 1. So M is a 1, R value T1 by T2, and N adiabatic polytropic index A bit 1.3 minus 1. So total we got as a 222 kilojoules. After that we have to calculate the heat transfer. So heat transfer or heat exchange per kg of gas is gamma minus n by gamma minus 1, where gamma is the adiabatic index. We all know that it is a 1.4, and n is the polytropic index, it is a 1.3, and work done we calculated previously in a B bit, it is a 222 kilojoule. So 1.4 minus 1.3 divided by 1.4 minus 1 into 222. So we got the 55.5 kilojoules, 55.5 kilojoules. So this is the problem based on the polytropic process. So first identify what is the process they given, and study the problem 2 times, and write the given data, and write whatever they asked, simply write and put question mark, and write whatever the formulas applicable to that problem. What are the formulas applicable to that problem? So here what we applied, so a relation between the first polytropic index, we all know that n is equal to log P1 by P2 divided by log V2 by V1. After that temperature T2, after that work done, after that heat exchange. So heat exchange formula Q122 gamma minus n divided by gamma minus 1 into work done. So previously we calculated the work done, that's why it is so easy to calculate the heat exchange or the heat transfer per kg of the gas. So it is a 55.5 kilojoules. So next move on to the another problem. A mass of air has an initial pressure of 1.3 meganewton per meter square, volume 0.014 meter cube, and temperature 135 degrees centigrade. It is expanded polytropically until its pressure is 275 kilonewton per meter square and the volume becomes 0.056 meter cube. Assume Cp value and Cv value. So here they given it is an expanded polytropically, but they didn't given the polytropic index value. So first we have to calculate that index value also by using the formula n is equal to log P1 by P2 divided by log V2 by V1. So by using that relation we have to calculate the polytropic index value. So before calculating that, first we have to write the given data and what they are asked. So a mass of air has initial pressure. So P 1.3 meganewton per meter square. So I am writing as a 1.3 into 10 square means 130 kilonewton per meter square. Volume 0.014 meter cube. P1 temperature 135 plus 273 302 Kelvin. It is expanded polytropically. PV power n is equal to constant until the pressure P2 is 275 kilonewton per meter square. The volume becomes as a 0.056 meter cube. Cp value, Cv value. So by using Cp and Cv values, we can calculate the gamma value and the R value. So gamma is equal to Cp by Cv and R is equal to Cp minus Cv. So first we have to calculate the mass, next final temperature, law of expansion. Law of expansion is nothing but PV power n is equal to constant. Work done, heat transfer, change in internal energy. So these are the, we have to calculate it. So first write the P1 is equal to 1.3 mega Newton per meter square, that is 1300 mega kilonewton per meter square. B1 0.014 meter cube, T1 135 plus 273 408 Kelvin. Assume polytropic expansion, P2 275 kilonewton per meter square, V2 0.056 meter cube. So these are the data given in the problem. So first line by line we solve the problems. So Cp and Cv. So first we have to calculate the mass of the air. So mass of the air is equal to, we know that the ideal gas equation Pb is equal to mRT. So from that I am using m. M is equal to P1 V1 by RT1. P1 V1 by RT1. So in the data they given the pressure value, volume value, and R can be found by using the R is equal to Cp minus Cv. R is equal to Cp minus Cv. T1 is equal to 408 Kelvin. So we will get the 0.1554 kgs. So mass is equal to PV is equal to mRT. So P1 V1 is equal to mRT. From that we will calculate the mass. Next to final temperature. So we in the problem they given the pressure values. So pressure values we can find after finding the polytropic index n value, we can using the relation between T and P, we can calculate the temperature. Otherwise by using the equation, and for the state 2, T2 is equal to P2 V2 by MR. So P2 into V2 divided by M, 0.154. In the first bit we got the mass 0.155, for R value 0.287. So T2 is equal to 345.23 Kelvin. So if you want in degree centigrade, simply subtract the answer with a 273 degrees centigrade, we will get 72.23 Kelvin, 72.23 degrees centigrade, sorry. So this is a final temperature of expansion is nothing but PV power n is equal to constant, n is equal to log P2 by P1 log V1 by V2. So in the problem they given all the values P1 and P2, V1 and V2. So simply substitute by using the calculator. First calculate the numerator. So that is what is the numerator for 275 by 1300, calculate that value. For that apply the log E answer, log E 275 by 1300, like that log E 0.014 by 0.056. So we got the polytropic index as a 1.12. So here you have to do the calculations carefully. First do the numerator, after that denominator, after that combine the numerator and denominator. So we got the polytropic index as a 1.12. Work done by the gas. So P1 V1 divided by P1 V1 minus P2 V2 by n minus 1. Substitute all the values, P1 value, V1 value, P2 value, V2 value. So after that we will get as a work done is a 23.33 kilojoules. So work done is equal to, here it is an expansion they given. So that's why we are wrote as a P1 V1 minus P2 V2 divided by n minus 1. If in the problem it is given as a compression, we can write it as a P2 V2 minus P1 V1 divided by n minus 1. But clearly mention that it is an a P1 V1 minus P2 V2 divided by n minus 1, because it is an expansion process. It is an expansion process. So next move on, heat exchange or the heat transfer, the Q. So here the polytropic process, both the work done and the heat exchange, heat transfer is there. So Q is equal to gamma minus n divided by gamma minus 1 into work done. So already in the d bit we calculated the work done. So simply substitute here the gamma value 1.4 and the index value we got, it is in a 1.12 divided by 1.4 minus 1 into work done. So this is the heat transfer during the polytropic process is 16.33 kilojoule. Change in internal energy. So according to the non-flow energy equation, we know that dq is equal to du plus dw. So here from d bit we got the w value, from e bit we got the q value. Substitute these two values here, we will got the internal energy. So 16.33 plus u2 minus u1 plus 23.33. So we will get the u2 minus u1, it is a minus 7. So minus 7 indicates that the internal energy is decreasing. Internal energy is decreasing. So in this class you learned about the adiabatic process, polytropic process and the numerical problems related to the polytropic process. So what are the formulas we learned here? Mainly are the three formulas, mainly four formulas. First formula is a work done, work done during polytropic expansion. So first one is the expansion. So W is equal to P1 V1 minus P2 V2 divided by N minus 1, or in terms of a temperature as a MR T1 minus T2 by N minus 1, where N is called as a polytropic index. So here in the heat transfer also Q is equal to gamma minus N by gamma minus 1 into P1 V1 minus P2 V2 by N minus 1. So these whole P1 V1 minus P2 V2 divided by N minus 1 we can write as a work done. So work done. So in terms of a temperature, we can write that in terms of a temperature also gamma minus N divided by gamma minus 1 as a MR T1 by T2 N minus 1. So the main difference between the adiabatic process and the polytropic process are that in adiabatic process the heat transfer does not takes place. So dq is equal to 0. Whereas into the polytropic process both the work and heat energy may be transferred across the boundary. So they can be described with the pressure and volume by any relationship, or they given the equation as a PV power n is equal to constant. So n is nothing but here called as a polytropic index or the polytropic exponent. So here also how will you calculate the n? Means here the n has one formula also, that is log base E P1 by P2 log E base V2 by V1, or these formula we can write, or simplifying is we can write like this also. N is equal to log E P2 by P1 log P2 by P1 divided by log V1 by V2. So base E, so we can write base E or base 10, both are equal on here, because E is equal to log base E we can write as a 2.3 log base 10. In the numerator 2.3 is there, denominator 2.3 is there. So both the 2.3 will get cancelled. So both log 10 P1 by P2 divided by log 10 V2 by V1. The next the relationship between the P, V and T. So like in adiabatic process, so in polytropic process also there is a relation between P, V and T can be represented same as in a adiabatic process by replacing gamma with an N, gamma with an N, where gamma is an adiabatic index, N is a polytropic index. So same formulas I am replacing gamma with an N. Here first formula is a P1 V1 power N is equal to P2 V2 power N. Second formula is a T1 by T2 is equal to V2 by V1 whole power N minus 1. So we can write this anyway. It's the simplification only. We can write this N minus 1 also bring to the left hand side. So then it becomes a T1 by T2 whole power 1 divided by N minus 1 is equal to V2 by V1. Like this temperature and temperature and pressure P1 by P2 is equal to T1 by T2 whole power N divided by N minus 1. So here I am combining the three equations, can be written as a V2 by V1 whole power N is equal to P1 by P2 is equal to T1 by T2 whole power n divided by n minus 1. So these are the relationship of the pressure, volume and the temperature. So in the next class we will discuss some more problems based on the polytropic process, and we and the various process on the we draw a PV graph of for the for five process. So what are the five process we learn? It is in a constant pressure process, means isobaric process, next constant volume process, next isothermal process, that is a constant temperature process, next isentropic process nothing but the adiabatic process, next one is a polytropic process, next one is a polytropic process. So these five process we can draw in a one PV graph and see what are the changes will happening in that graph. So in the next, thank you.